Hello everyone, this is Dr. Alok Agrawal and I welcome you all on the fourth lecture of course Fluid Mechanics having course code ME404. So in this lecture we will study another fluid property known as viscosity, and this is very important property of fluid which we will be using throughout the course of our class. So before going into the viscosity, let us first understand a concept that is known as no slip boundary condition concept. So here I will be explaining you this concept because this will be helpful for us for developing the definition of viscosity and to understand viscosity in a better way. So what is happening here? See, let us assume that the fluid is flowing with a velocity u infinity. Okay, here the notation used for free stream flow is u infinity. So I am also using the same notation. Now suppose here we can see that each layer of fluid is having the velocity that is equal to u infinity, and this velocity is known as free stream velocity. Now suppose that in this flowing stream I inserted a plate of having certain width and length and with negligible thickness. So what will happen? The layer of fluid which directly comes in contact with this plate, this negligible thickness plate, will gain the velocity that is similar to the velocity of this plate. And in this case, the velocity of plate is zero. So the molecules that come in contact with this plate will try to stick to the plate and will gain the velocity that is equal to the velocity of plate. That is zero. Now see what will happen next. The fluid will attain the velocity of this plate and it will not going to slip over this plate. They are not going to slip over this plate, and because of that, this we assume that the molecular fluid will not slip over this plate, and this concept is known as no slip boundary condition, where the fluid will attain the velocity that is similar to the velocity of the plate. Now suppose if the plate is moving with certain velocity other than this free stream velocity. So in that case, what will happen? Again, I put this plate in a free stream velocity flow having some velocity. The velocity of plate is suppose capital U. Now what will happen then? The fluid that comes in contact with this plate will attain the velocity same as that of the velocity of plate, and that is capital U. So again, the layer which is directly come in contact with the plate is not slipping over the plate. It will attain the velocity of plate. It will stick to the plate, and that phenomena is known as no slip boundary condition. Okay, so with this phenomena, we will study the property viscosity. So first, we have seen no slip boundary condition. Now we'll see the viscous effect. What effect it creates? So we have seen that the first layer which come in contact with the wall or the plate directly will tend to stick to the plate and will attain the zero relative velocity. Why it is happening? Because that layer of fluid will directly feel the presence of the wall. Okay. Now let us talk about the layer which is just above the first layer. So the layer of fluid which is located immediately above the first layer will not directly feel the presence of the wall. It will feel the effect of wall or the presence of wall by virtue of some fluid property. And what that fluid property is doing? That fluid property enables the effect of momentum disturbance imposed by the wall to propagate from the wall adjacent layer to the further outer layer. What does it mean? That the fluid layer which is just above the first layer will not feel the presence of wall directly, but it will feel the presence of wall by that first layer. Okay, the first layer will feel the presence of wall directly, and with the help of that first layer, the second layer is feeling the presence of wall. So what will happen? That first layer will try to decrease the velocity of that second layer of fluid as well. Earlier, both the fluids will having the same velocity u infinity. Okay. Now, when we kept the plate, the first layer will come in contact with the plate and attain the velocity of that plate, that is 0. Now, the fluid which is just above the first layer of plate, it will not come in contact with the plate, but it will feel the presence of plate by virtue of first layer, and because of that, the velocity which is earlier u infinity will decrease. Why? Because first layer will try to decrease the velocity of the above layer. And the property by which this first layer giving resistance to the movement of the second layer is called viscosity. Again, as we move further away from the plate, the velocity of layer will increase. Okay, first layer velocity is 0 because of plate. Again, 0 plus something, second layer velocity, again the velocity will increase and increase and increase when we move away from the plate in y direction. Okay, and there after some time, after some distance, there point reach where the fluid again attained the velocity which was earlier, that is free stream velocity. Okay, and is that point defines where below which there will be a viscous effect and above which there will not be any viscous effect. That is, above that point, above that point where the velocity of fluid will reach the free stream velocity is called inactive zone, where the effect of plate is not felt, and the point below which there will be a difference in velocity in each layer is called active zone, where the effect of plate is felt. So there is a two zone, active zone, which is also called viscous zone, and there is inactive zone, which is also called non-viscous zone. So in this course, we'll be talking about viscous zone, active zone, where the viscosity effect is there, where one layer give or provide resistance to the another layer. Okay, so with this we can define the viscosity now, and we can define viscosity as the property of a fluid that offers resistance to the movement of one layer of fluid over another adjacent layer of fluid. Okay, so here viscosity is defined as resistance. Okay, again we have seen in viscous, we have seen that one layer is trying to resist the movement of second layer, and again that layer will try to resist the movement of its upper layer or its adjacent layer, and that resistance is known as viscosity. I hope the definition of viscosity is clear. Now let us move to the Newton's law of viscosity, that is very important. So I have taken an element, fluid element of say rectangular shape or square shape inside the viscous zone or active zone. These fluid elements belong to the active zone. So in that active zone, what is happen? There will be a difference in the velocity of the two layers. So let us see, let us suppose that the velocity of lower layer is u and the velocity of upper layer is u plus du, something greater than the velocity of lower layer. The velocity of lower level is low because it is feeling the presence of wall more or higher as compared to the velocity of upper layer. So here the velocity of lower layer is u and the velocity of upper layer is u plus du, and where du is a very small quantity. The distance between the two layers is dy, which is also very small. Now see what will happen to this element. After a very small interval of time dt, very small interval of time dt, what will happen? The upper layer is moving with a velocity du higher than the velocity of lower layer. So after a very small interval of time dt, the upper layer will cover somewhat more distance as compared to the lower layer. So this square element changes its shape and it will become like this, that is rhombus shape. Okay, So there will be a deformation. There will be angular deformation of this element, and that deformation is d theta, which is again very small because we have taken very small interval of time dt. So we can say that the upper layer moves ds distance more as compared to the lower layer after very small interval of time dt. Okay, so now see what is happening here. This d theta is known as shear angle, and shear strain is measured by this shear angle d theta. Now let us apply trigonometry in this triangle. Okay, so from here we can say that tan d theta is equal to ds by dy. ds is perpendicular, dy is base. So tan d theta is ds by dy. Now what is this ds? This ds is a distance which is also the multiplication of velocity and time. So the velocity of this layer is du more than the lower layer. The velocity of upper layer is du times du more than the lower layer. So relative velocity is du between these two layers, and the time is dt that we have taken. So this ds distance is du into dt and divided by dt dy. So tan d theta can be written as du into dt by dy. Since we have taken very small time dt, so this d theta is also very small. So when this is very small, we can write tan d theta as d theta only. Okay. So the rate of angular deformation or the rate of shear strain gamma can be written as d theta. We can take this dt and we will bring this dt below d theta. So this rate of shear strain gamma can be defined as d theta by dt, which is equal to du by dy. So this gamma is known as rate of angular deformation or rate of shear strain. Okay. Now the top layer causes a shear stress on the adjacent lower layer. Similarly, the lower layer also causes a shear stress on the adjacent top layer. Okay. This upper layer will try to increase the velocity of lower layer. This lower layer will try to decrease the velocity of upper layer. So there will be a shear stress, that is upper layer causes to the lower layer and lower layer causes to the upper layer. And this shear stress in the fluid will be a function of rate of shear deformation. So we can write tau is proportional to gamma, that is tau. When we remove this proportionality sign, we have to insert a constant of proportionality. Here we have inserted mu. Tau is equal to mu into gamma, where gamma is du by dy from this equation. So we can get tau is equal to mu du by dy. And this is known as Newton's law of viscosity. This equation is known as Newton's law of viscosity, and this constant of proportionality mu is known as coefficient of viscosity, or we can say that simply viscosity, and it is also known by other name known as dynamic viscosity. So this mu can be said coefficient of viscosity or dynamic viscosity. And this equation tau is equal to mu du by dy is known as Newton's law of viscosity, which is very important because we are going to solve various problems with the help of this equation. Thank you very much. In next class, we'll see what are Newtonian fluid, non-Newtonian fluid. We'll see the unit of viscosity, and we will see what are the various types of fluid. Again, we will also see the kinematic viscosity. Here, mu is dynamic viscosity. In next class, we will see what is kinematic viscosity. Okay, so thank you.